All right, this is Advent of Code, day 19, unofficial. Here we go. Beacon scanner. As your probe drifted down through the water, this area released an assortment of beacons and scanners into the water. It's difficult to navigate in the pitch black open waters of the ocean trench, but if you can build a map of the trench using data from the scanners, you should be able to safely reach the bottom. Oh man, I hate building up maps. The beacons and scanners float motionless in the water. They're designed to maintain the same position for long periods of time. They float motionless in the water. Each scanner is capable of detecting all beacons in a large cube, oh no, centered on the scanner. Beacons that are at most 1,000 units away from the scanner in each of the three axes have their precise position determined relative to the scanner. However, scanners cannot detect other scanners. The submarine has automatically summarized the relative positions of beacons detected by each scanner. 719.input. All right, so we have 37 scanners, and these are all the other things that it has detected. Okay, for example, if a scanner is at XYZ, coordinates 500, 0, and negative 500, and there are beacons at whatever, the scanner could report that the first beacon is at negative 1,000, 1,000, negative 1,000, but would not detect the second beacon at all. Got it. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, the scanners do not know their positions. You'll need to determine the positions of the beacons and scanners yourself. Scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions, such there are, by finding pairs of scanners that have overlapping detection regions, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scanner at a time. 12 common beacons. For a moment, consider only two dimensions. Suppose you have the following scanner reports: 0, 2, 4, 1, 3, 3. Drawing X increasing rightward, Y increasing upward, scanners as S, the beacons as B, scanner 0 detects this, scanner 1 detects this. Assume scanners only need 3 overlapping beacons, then they overlap to compute this visible map. Unfortunately, there's a second, oh my God. Holy crap. There's a second problem. Scanners don't know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns around all of the X, Y, and Z axes. That is, one scanner might call a positive direction positive X, while another scanner might call that direction negative Y. They might agree which direction is positive X, but one scanner might be upside down from the perspective of the other scanner. In total, each scanner could be in one of 24 different orientations facing positive or negative X, Y, or Z, and considering any of 4 directions up from that facing. Here's an arrangement of different beacons as seen from a scanner in the same position but in different orientations. By finding pairs of scanners that both see at least 12 of the same beacons, you can assemble the entire map. For example, considering the following report. Because all coordinates are relative, in this example, all absolute positions will be expressed relative to scanner 0. Using the orientation of scanner 0. Scanners 0 and 1 have overlapping detection cubes. The 12 beacons they both detect are at the following coordinates. Orientation of scanner 0, and as if scanner 0 is at coordinates 0, 0, 0. Okay. Is it exactly 12? How many beacons are there? Holy cow. Grouped stirs. Scanners equals grouped stirs dot map do scanner data beacons equals scanner beacons 27. So all right, 56 divided by 37. So each scanner sees about 30 beacons, 28 beacons, which is 28 times 27, 378 different pairs of beacons. So I think I'll basically just like take all of the deltas, map them to absolute values, and sort them, and then see how many overlap, and just like start there. Scanner data dot map do line dot split map to I scanner beacons. Scanner deltas equals scanner beacons dot map to beacons beacons each do beacon 1 deltas next if beacon delta sig equals beacon 1 map deltas scanner deltas okay, and now I can just figure out the overlaps of them. Scanner deltas dot each do scanner 1 delta's 1 with index S1 overlaps require set new count. Delta's 1 and next if S1 equals S2. Next if delta sig equals 0, 0, 0. To count S1, S2. Overlaps dot sort overlaps num intersection puts found overlapping sigs between S1 and S2. Line 30. This huh. .ex1 chords equals wow. Okay, found 3 overlapping signatures between 0 and 1. Let's see. X, Y1, negative 618 minus negative 537, dx1, dx2 equals 824 minus 823, dx3 equals 621 minus 458. wait. dx1 equals 618 minus 537. And now here we have, y1 equals 686 minus 605. dy2 equals 422 minus 423. 3 equals 578 minus 415. Map abs dot sort. Scanner Delton. Puts delta seg. With index. S. Puts scanner delta seg between and B2. Okay, yeah. Nineteenth EX2. Oh, that's why. Okay. 66 overlapping signatures. Puts overlaps dot count. $110. Okay. So I can basically modify this and make a signature set, which will be, oh, also I can multiply these by oh, wait, 66 signatures, 12 times 5 times 11. Oh! 44. Okay. Let's do this. 1, 2, 3. Okay. So, So we don't have the mirror orientations. We only have the num overlapping equals 12, required intersecting deltas Okay. Scanners 0 and 1 have Okay. So that's mostly, I think that's done. Those are the overlapping ones. And now okay. Okay. So now I need to figure out which rotation, basically, which of the reconfiguration gets them to overlap correctly. Okay. So, overlaps equals overlap map each do overlap hash.new. Overlap map S1, S2. Normalized equals set.new S1. Normalize sibling, normalized neighbors to normalize equals overlap map dupe. While to normalize.any oriented to orient. Next equals to next to orient equals to orient. Pop. Next if oriented dot include next to orient. Orient scanner deltas map neighbor relative to next relative to oriented next to orient. Oriented beacons equals orient relative orient overlap scanner deltas next to orient scanner deltas relative to scanner deltas next to orient oriented beacons. Def orient delta beacons 1 beacons fixed oriented Scanner deltas. I want scanner beacons. All right, so we need to find the find 12 overlapping beacons. Def find 12 overlapping beacons. B2. Def delta. DS1, DS B1, map do beacons. Deltas sig to indexes equals sig to indexes sig to indexes something delta and map 1 deltas and map 2 deltas 1 map 1 equals deltas and map 1. Okay. Deltas equals deltas 1, 2. Beacons 1 equals deltas dot flat map D map 1 D Okay, so that gives the 12 beacons, but it doesn't give their... Aha, okay. So now I can take... Oops. So that gives me List 1 equals beacons 1. List 1 equals sig to indexes delta 2. Beacons to delta. Beacons to delta B1. Sig to indexes beacons to delta. Beacons to delta 1. Beacons to delta 2. Beacons 1. Overlapping beacons 1, overlapping beacons 2. Puts overlaps. Solution. puts to orient.inspect Okay, that makes sense. That should not be 66 though. Overlaps. Okay, so it's how many overlap. Did I miss something here? No. Okay. Overlap map. Overlap map. Overlaps.each do S1, S2 overlap map S1. Overlap maps. Okay, yeah, that's what I wanted. Perfect. Holy cow, 44 minutes. This is I'm moving along. 35. Sig to indexes. To indexes 1. 52. Oh. $658, $858, -$460. Perfect. Okay, so I have the things. Okay. Possible starts equals beacons sig to indexes 2 of beacons to delta first delta equals beacons to delta of overlapping delta possible starts dot each do do list 2. Index equals 1. Next index equals 2. While next in is less than num overlapping. Delta 1 equals beacons to delta 1 prev beacon 2 equals list 2 dot last. Beacons for delta equal sig to indexes 2 delta. This is adjacent delta. Beacons for delta, sig to indexes 2. minus minus prev if no next beacon puts picked wrong start. Next. Break. Next if list2.length not equal. Return something. Picked wrong start. Otherwise, next beacon equals beacons for delta. List2 overlapping beacons 2. Worst due to, I'll answer you in a second. I need to get to sort of a stopping point because I have a lot of stuff in my head right now. Overlapping beacons 2 beacons for delta. For delta.inspect. Not equal 1. Overlapping beacons 2. List return list 1, list 2. Puts each puts b.join relative to beacons orienting beacons. Oh. Next index plus equals 1. $14. What do I think about people who get 2 full-time jobs and salaries and just do the minimums on both to not get fired? Pretty shitty thing to do. He should work for a better company. Okay. Puts list one dot each puts list one dot join. Uh, 15. Oh, puts. There we go. Okay, so the way I'm trying to do this is I just get the overlapping ones from the first one. I get the overlapping ones from the second. Okay, cool. That's what I expect. So I get the delta between the first and the second. What's possible starts. Picked wrong start. 3, 4, 1, 3. Okay. Is this right? Why is it 0 and 1? That seems wrong. $15.19. So then, so I get the possible starts. Which are sig to indexes. To array. Puts sig to indexes 1 dot inspect is this what I expect? Yeah, that's roughly what I expect. So zero 81. Count. Are these the right size? 300. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's 24 over 2. Okay, yeah, that's the right size. Puts deltas dot to count. $66. Oh. Prev beacon. $15. Do 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 do. Done. What the heck? Okay, now it works. 82. Puts $13. Zero, 1. Possible starts dot each. Overlapping beacons too. Next index. Okay, next index. Next index. 1 minus 1, 0, and 1. Beacons to delta. Puts adjacent delta. Okay, I think I'm definitely doing way more work than I need to, but whatever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Oh. Okay, it worked. Relative to becomes 90 and then 528. So this should be the fourth, negative 336, and then 460. Perfect. Okay. Beacon beacon 1 B2 equals beacons orient. So now we need to find which orientation produces the same delta. So 0, 1, 2 dot permutations and then 2 to the 8. Right. So yeah, so that's 24 possible things. Each do order oriented each do flip X delta equals orientation mod equals order flip X if orientations, if deltas match beacons, oriented beacons, orientation mod, return beacons.map orient beacon orientation mod orientation mod def orient beacon orientation mod beacon equals if flip X Z beacon I1, I2, I3 equals orientation mod order def deltas match B1s, B2s, orientation mod, B1s, each cons 2. Wow, this is amazing. In Ruby, I can do this. Each cons 2.zip b2s.each cons 2 do b1 pair b2 pair b's oriented b's B pair, oriented B pair, B1, B2 equals B pair, orient beacon orientation mod. OB OB1, OB2 equals oriented B pair all B1 D1 delta 1 B1 Yeah, each cons is great. Delta equals oriented delta. Orientation puts oriented next mod. Puts orientation mod dot inspect. To 11. Permutation. False, true. Deltas match. Puts B pair checking puts B1 So let's make sure this goes. So 210 should flip the order. And we're taking the negative of each thing. Puts delta 1, delta What am I doing wrong? Because I'm getting the same delta each time. Oh. Wait, none of these are ever equal? Wait, what? Wait a second. So this is the reoriented one. This should be negative 1310. How do these end up the same? Oh no. Puts matched if delta equaled aha, it worked. Okay, perfect. I did it. No, I do not. You spend an hour and a half at a certain point, you're like, I don't really want to spend any more time on it. Okay, so I've oriented all of them. And now I need to figure out the displacement between them. Displacement. The displacement will simply be beacons orient all the beacons dx equals beacons beacons each beacon plus equal dx z so I want new x equals x plus dx equals ox. So dx equals ox minus x. Oriented beacons beacons equals set dot new scanner beacons dot each do beacons dot each do puts beacons dot size. Huh. Puts oriented relative to orientation mod dot inspect. No. Do 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 try to orient and then I need to add all of its things. Overlap map oriented dot each do neighbor oriented. Now, where am I getting stuck? To orient $247. Oh, all beacons. $252. Put to orient dot inspect. Puts already oriented next to orient, puts oriented 0. Oh, next to orient. There we go. No. How do those get turned into sets? Next to orient. That's how. $239. Put scanner beacons. $132. Original beacons. Original beacons. Holy cow. What just happened? Hello, people. Original beacons. Who are all of you? What just happened? I don't know what just happened. What happened? Who are all of these people? Let's do this. New beacons. Does anyone know what just happened? Why did I get 1,000,000 hellos? Oh. $123. Okay. I don't know if that worked. Oriented beacons dot zip beacons dot each do put beacon Man, that was wild. Okay, that's wrong. Because this should still be first oriented beacon. 127. Okay, that's not working as I expected. I do not. I don't exactly know what. I know that they exist. I forget what the difference is between them. These were supposed to reorient things and get the same points. And I'm not sure why that didn't happen. Puts orient beacon orientation mod. Puts original oriented reoriented. So this is like, where's the 404, 528? Wait, 404 minus 528. -178 -336 minus 460. That doesn't make any sense. Wait, 404, 528 is the 4th and the 6th. 4th and the 6th. And these should now have the same deltas. Puts trying. Unoriented. So I flip the Y, that's it. Or no, I flip the X and the Z. So 404 minus 528, -124. -336 minus 460. 124. Wait. Reoriented. What would, wait, if I flip the X and the Z, that's basically rotation by 180. What does that even mean? I think I just need to check the different orders. Or do I just not include flip Z? Oh, oops. All right, now I am realizing I don't know if I've done the problem correctly. Puts found work. It worked. Oh. I guess it does work. Wait, no. Okay, this should work. If deltas match. Oh, because that's why. Okay. Puts let's just add some more dupes in here. This should not be 740. Ha. Woohoo! It worked. 462, let's go. I did it. This is all for testing. Where are these puts coming from? Okay. Okay. Largest distance equals 0. Largest distance equals part 2, largest distance. Oh no. Damn it. I did cumulative offsets. Ba. Why? Oh my god. Damn it. Oh, I don't. This sucks. Displacement. Scanners equals looks equals max distance equals 0. Part 2, max distance. Let's go. Woohoo! I did it. Oh, I did it. That took a while. That one was difficult. Oh. Man, I guess thank you for, sticking around, G-Man. But why did you just watch me do that for 2 hours? Like, yeah. I don't get it. Watching multiple streams? Okay. Let's go over this problem and talk through my solution. All right, day 19, beacon scanner. As your probe drifted through this area, it released an assortment of beacons and scanners into the water. It's difficult to navigate in the pitch black open waters, but if you can build a map of the trench, you should be able to safely reach the bottom. Beacons and scanners float motionless in water, designed to maintain the same position for long periods of time. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. Beacons that are most 1,000 units away from the scanner and each of the axes have their precise position determined relative to the scanner. However, scanners cannot detect other scanners. Submarine has automatically summarized the relative positions of beacons detected by each scanner. Your puzzle input. For example, if a scanner is at XYZ, whatever, here's an example. Scanners do not know their own positions. You can reconstruct the regions. The scanners and beacons map a single contiguous 3D region. The region can be reconstructed by finding pairs of scanners that have overlapping detection regions such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other. So there's this example in 2 dimensions where here's a scanner and here are 3 beacons that it sees. Here's another scanner and here are 3 beacons that it sees. And those are like the same beacons, so these are where the 2 scanners are. Unfortunately, there's a second problem that the scanners don't know which direction they're looking, but they're aligned along an axis, and they don't know like rotation. So it's basically 24 different possible rotations because they're not going to be mirrored. Anyway, that's how it works. So we have to find pairs of scanners that see at least 12 common beacons. And then we can use those to like orient them relative to each other. And that does stuff. So how do we do this? Well, this is how I did it. Yeah. No. Go, where are we going? 50. All right, here's the start of my solution. So we get all of our beacons. Pretty simple. Here's what the input looks like. First line is the scanner number and then a bunch of numbers, 3 numbers separated by commas. So for all my scanners, I get all of their beacons in an array. Then basically what I thought was you can just compute, you can like create a signature of the, basically you want it like, if two cameras are looking at the same 2 sets of beacons, regardless of or 2 scanners are scanning the same 2 beacons, regardless of the orientation, the displacements between their 2 beacons, the delta between them, basically like the absolute values, basically depending on their orientation or whatever, like the values, the absolute values of the displacements could be off, and the order could be off. Like the axes could be off if it's like rotated. Yeah, depending on the orientation, basically like the deltas could be like negatives, opposites of each other, and they could also be reordered. And they're basically like, there's 6 ways to arrange the 3 things, and then you can choose to flip each of the 3 values. Live coding, thank you for the follow. So that's 6 times 2 times 2 times 2. So 48 different possibilities. Half of those will refer to impossible. Half of those will refer to mirrored orientations, but that doesn't matter. So we'll basically take all of the displacements, all of the pairwise deltas, and normalize them to the version that they're increasing and they're sorted and they're all positive. So I'll take the absolute value and sort them. And that'll give me all like the normalized delta signatures. So that's what this is. Over each beacon set, I loop over all the pairs of beacons, create the signature, and then add that to a set of signatures. So that gives me all the delta signatures. Then I just I go over each pair of scanners and see how many signatures overlap with the other signatures. How many of these canonicalized signatures for each scanner overlap with the canonicalized signatures of another scanner. Turns out that if 2 things can see 12, if 2 things both see the same set of 12 scanners, then that's 12 times 11 divided by 2. So 6 times 11, 66 different deltas between all of those same sets of scanners. So we figure out the overlaps of each pair of scanners, how many things they both see, and then the 2 scanners themselves. And I select the ones that have more than the number of required intersecting deltas. And it turns out that that's just, those are all the pairs of scanners that like see some of the same space. So then I need to basically orient all of those. So I'm basically going to say that scanner 0 is correctly oriented and it's at position 0, 0, 0. Then for every scanner, I can see what scanners it's also oriented. It also like intersects with. And then I can take that scanner, figure out how to orient it properly, reorient it relative to the origin, to the first scanner, and then I can like reorient its neighbors. So I have all of this overlap map is which maps overlap, which scanners overlap with which other scanners. And so I'm going to say that I have one set that's oriented, one thing that's oriented. And the things that I have to orient are all of the neighbors of scanner 0, and I have to orient them relative to scanner 0. And I'm also going to keep track of these, which is part 2. So while I have any things to orient, this is the next scanner to orient, and what I'm orienting it relative to. I'll skip if I've already oriented it. Say that I've oriented that thing. So then I need to orient that thing, and that'll return like a new set of beacons for it. I get the beacons for the thing that I want to orient and the beacons for the things that has already been oriented. And I update the beacons for the new thing. Then I'll say that I have to orient all of the neighbors of the thing that I just oriented. So pretty simple breadth first search, I guess. Yeah, breadth first search. So how do I orient the beacons? So this is how I orient the beacons. So I basically first find the 12 overlapping beacons between the two sets of beacons. And I first, so I do this basically very similar to the other stuff that I did, where for each set of beacons, I'm going to create a set of all their deltas. I'm going to also create a map from each like canonicalized delta signature to the deltas for that, to the beacons that, to the pairs of beacons that have that signature, and then also from each pair of beacons to their signature. So I create all of their signatures and add that to the delta set, and then also set up these maps. So now for both these two sets of scanners, for these two sets of beacons visible by these two scanners, I have all of the deltas between each pair of beacons for each scanner, and then I have a map from each pair of beacon to its delta and each delta to the beacons between them. So then I overlap the deltas, and that gives me the deltas between the beacons that are also visible to the other scanner. So then to get the actual overlapping beacons, I take all the deltas, I go from the delta signature to the beacon indexes, which is basically, this is like the weight of an edge to the nodes at the end of the edge. And so it's the two nodes, and so I flat map to make it a flat map. And then I unique all of it, because this will give me 66 edges and it'll give me 132 actual nodes, but I want to unique it, so it's just 12. So I'm gonna, now I have all of the edges. Now I have the 12 beacons for one scanner. Now I want to figure out, I want to get those same 12 beacons for the other scanner in the same order. So I have the 12 beacons for the first scanner. I just pick the first two beacons and I figure out what their delta is. And that gives me two beacons. That tells me that these two beacons in the first scanner set map to these two beacons for the second scanner, but I still don't know which one's which. So I get the two beacons for the second scanner, which is here. And now I'm going to basically try to build up that same list by looking up the distances. And I'll do that. I'll try starting at both things. So now I'm building up the set for the other scanner, the set of beacons for the other scanner. So I have the next index, and I'll get the previous beacon. This was the delta between, like the first time I go through this, this is like the delta between 0 and 1 in the first beacon set. And so now I want to find the two beacons that have the same delta for the next beacon set. So yeah. So that's the delta that the first beacon. Wow, this is so confusing. Basically, like I have this, if you imagine the 12 beacons for the first beacon set, I can basically like draw a line. I basically have some ordering of them, and I have the deltas in between all of them. And I'm trying to basically like rebuild the same map in the second beacon set. So I have an edge, and I see, okay, this edge is this length. These are the two edges in this set that have that length. And so I have the two that start for the first beacon set, and then I have two possible starters for the second beacon set. So I pick one of them at random, or I try them both, and then I say, okay, I get the length of the next edge for the path that I'm trying to create, and then I get all of the beacons, the two beacons that have that length for in the other set. And ideally, if I'm creating the correct path, those two beacons will include the previous beacon that I just looked at. So I get the beacons for that delta, and I get rid of the previous beacon I looked at. But if I picked the wrong start, then the two beacons that have that delta, neither of them will be the beacon that I picked. Neither of them will be the last beacon. And so I'll have picked the wrong start, and so I'll just break so that I try the next one. But otherwise, this builds up all of the beacons for the second set. And then I actually map, this is like technically their indexes, the type, keeping track of the types of, in this one was a real doozy. So I map over all the beacons and the indexes to get the actual beacons. So that finds the 12 overlapping beacons, and that will be in the same order. So now, do I use that ever? Okay, these variables are unused. So now I need to figure out how I need to reorient the beacons. So I go through all the permutations of ordering the three index axes, and then whether I flip the three axes. And this is the orientation mod. And so then I'll check basically if all of the deltas between each one match exactly. Not like the normalized delta signature, but the actual delta, the pure delta, once I've applied the orientation mod. So first I have this orient beacon. Given an orientation mod, I first flip the three values if I need to. Also, this modifies the beacon, which caused problems. But I flip them if it says to, and then I reorient them. So for the deltas, to see if they match, I'll iterate over each pair in the first beacons, along with each pair in the oriented beacons, and I'll orient the first beacons and make sure that all of their deltas, I'll apply the orientation to the first beacons, and if the deltas now match, that's good. And so I want the one that all of them match. I don't think I really need this all. I think I could have just checked the first one, but whatever, this like also worked. So once I find the orientation that gets all the deltas to match, then I can apply the orientation fix. So I first orient all of the new beacons. All right, take all of the original beacons, not just the 12 that overlapped, but all of them. apply the orientation fix. And now I need to apply the displacement to get them into the same positions as all the others. So I'll add here, want to do old beacon plus dx equals new beacon oriented beacon, therefore dx equals oriented beacon minus beacon. So I need to figure out the displacement, and then for all of the beacons I'm going to add that displacement. So I'm doing beacon, I want beacon plus the dx to be the oriented value. So dx should be the oriented value minus the original value. So I take here, now it's really crucial that I have two beacons that I know are the same. And so I take, this is looping over all of the beacons, including the ones that didn't overlap. But here I want that particular one that overlapped. So I take the first reoriented beacon, first overlapping beacon actually. I reorient it, and then I figure out the displacement for the X, Y, and Z. And then I return the new beacons and the orientation mod and the displacement. So this displacement is actually great because after I apply the overlapping, this tells me where, now I have all the cameras facing, because I orient everything relative to the first camera. And so then I fix it. And so then when I orient another thing, even if I'm not orienting it relative to the first camera, I'm now orienting it to something that is now in the same position as the first camera. And so I basically get all the cameras to face in the same direction. And then the displacement is exactly the position of that scanner. And so I orient everything, and then when I orient it, I also get the displacement, which is the location of the scanner. So then the actual two parts of the problem are, for part one, how many beacons are there? So now that I have the updated beacon locations that are all in the same coordinate system, I can just create a set of all the beacons, and for all the beacons for each scanner, I can go over all its beacons, add that beacon to a set, and then I just need to print out the size of that set. And then part two is what's the largest Manhattan distance between any two scanners. So I just loop over all the scanner locations pairwise. Skipping, this actually doesn't matter because I'm getting the max distance, and then I just compute the Manhattan distance, which is take the absolute value of all the deltas and then sum them, and then update it if need to. And that is the max distance between any two scanners. Yeah, right on. Cool. So that is Advent of Code 2021, day 19.